rookie mistakes on the other one, but we can get them here. Again, I'm not talking about A and D or hovering. All I've done is I've drawn box A with room to work, I've drawn box B with room to work, I've drawn the ground with room to work.
Did you intentionally make the boxes different sizes?
Not necessarily.
Okay.
Can we get rid of anything? Hey, we're left with these. See how easy this is? We got rid of 60% just by thinking.
Yay.
You just can't count on the fact that we can eliminate 60%, but we'll just pretend for right now it's that easy. Okay, so I think gravitational force is the simplest one. So let's start out with gravitational force. I do recommend that you do it force by force as opposed to object by object, but you know, whatever way your mind is working at the time you need to do it. All right, so which way is the gravitational force acting on what?
A and B are the gravitational is acting down, pulling them down.
So on each?
Yeah.
So I got weight, weight. We're missing something.
The ground is pushing up, pulling.
The ground's being pulled.
Yeah, the ground is being pulled up.
Yes.
So
Is there-
so I draw one arrow, two arrows?
I don't know.
Let's do two.
You going for two?
Yeah.
I heard two over there. W. All right. There is a mistake. It's not going to require any massive change if you're writing it in ink, so you don't need to worry about that. But there is a problem here. What is the problem?
Wouldn't the boxes be pushing against each other for some reason?
Yeah, but that's not a gravitational pull.
I mean, there's air pressure, but you said we weren't doing
Yeah,
that.
we're worried. The issue is what is drawn up here already, not what's missed, not the other forces.
The ground is not pushing against box A because they're not touching.
Right. The ground is not pushing against box A. It's not touching box A. That's fine.
Is the gravitational pull, like the way you drew it on A, does that signify by any means that it's being acted on by box B? Like, do you have to be more clear in how you draw the arrow on box A to show that it comes from the ground?
It's not how I'm drawing the arrow. The arrow is fine.
Do you need to like label the arrows?
If I leave it like this, I am making the claim that A and B weigh the same amount. And there's no reason to think that they weigh the same amount. I need to differentiate between them. So, box A, WA, WB, WB. And it doesn't matter which one's A and which one's B on the ground. This is how we indicate the fact that there's gravitational forces between A and the ground.
So, weight sub blank
Yes.
just signs into something.
So rookie mistake number 3, leaving subscripts off. What I do on there would be probably the next to last problem on the second test. I will, if you leave subscripts off, I'll give you credit for the first pair and then take off for the rest of them. But isn't there a gravitational force between A and B?
Yeah,
Why am I ignoring it?
because they're not significant enough.
The gravitational force, this planet here is on the order of 10 to the 24th kilograms. Small objects, my mass is about 100 kilograms. Elephant, even if you multiply it by a factor of 20, it's still tiny compared to that of the Earth.
I mean, that's like, is that, okay, I'm pulling chemistry into this. So, it's irrelevant in the way that like the mass of electrons are irrelevant to anything else, right?
Yeah, I think that's a appropriate analogy. If you bring into the gravitational force between A and B, it's gonna be on the order of somewhere around, depending on what the masses are here, but 10 to the negative 11th newtons. 10 to the negative 11th newtons. So that's a whole bunch of zeros before you get to the first digit. If you're gonna worry about that, then why not worry about the top half of A and the bottom half of A? Or maybe the upper right quadrant of A and the lower left quadrant of A, or a molecule and another molecule. It's a path to madness. Yes, Steph?
So this won't be on the first test?
No, this is second test stuff.
Just clarifying.
So rookie mistake number 3 was no subscripts. Rookie mistake number 4 is putting W sub A up on B. That would imply, if this force right here were up on B, that would imply if B disappeared, that gravitational force would disappear and A would just hover. Which is not my experience in life. Perhaps you have different experiences. But as far as physics is concerned, gravitational force is between the small object, or the weight is between the small object and the planet.
Because we're not working with magnets.
Say it again?
Because we're not working with magnets or anything. Yeah.
With what?
That would-
Magnets.
Magnets.
Oh, yeah, not yet, that's outside the scope of this course. All right, so gravitational force done. Normal force. Which way is the normal force act to normal what?
Well, ground's pushing up on B, and B's pushing up on A.
So I got ground's pushing up on B. And let's do the pairs. What's the other part of that pair?
Box is pushing down on the ground.
All right, then you said B is pushing up on A. Where's the other part of that pair?
A is pushing down on B.
And done.
That's a lot of arrows.
We'll eventually get to a test level problem where the number of areas is gonna be anywhere from, it's typically somewhere between 30 and 40 arrows.
Wait, what?
I'm gonna need some.
We're working our way there.
How big a paper will I need?
Did you just say 40 arrows?
8.5 and 11, I present it to you.
How much room of the paper? Half a page? How big should I draw it so it's comprehensible?
We'll get there.
So how do you, I was gonna say, how do you even read that?
We'll get there. Or are you referring to this or the one with 30 to 40
No,
arrows?
30 to 40.
Well, I'm hoping the students draw very neatly and don't do the rookie mistakes. But sometimes it is very difficult.
You poor dear.
Is that?
You poor dear.
Oh, yeah.
No, it's like color markers might help with the steam stream stuff.
Okay. There's actually an application to this. So, any questions on this before we get to the application?
No.
All right, I think at this point, hopefully we're comfortable enough with this that I can erase it. All right, so we're gonna take our box on ground and have person on scale on ground. So first I'm gonna draw the problem. I got ground, I have scale, I have person. So to do my force diagram, I draw the person, I draw my scale, I draw the ground. And then I just do my force diagram. It's gonna look very much like that. I'm gonna change the subscripts because to make them more specific to this problem. So instead of A, I'm gonna use P for person. Instead of B, I'm gonna use S for scale. So I have weight of person, weight of person, weight of scale, weight of scale, normal force on person, normal force from person. Normal force on scale. Normal force from scale. All right. So that is the same as this, just different subscripts, different stick figures. So here's the question. What does the scale measure?
Wait.
Nope.
Grams or kilograms?
It's measuring the normal force between the person and the scale.
Yes. This is the gravitational force. This is the weight of the person. The weight of the person is acting on the ground. The weight of the person is not acting on the scale. The only force that the person exerts on the scale is, as Talon said, the normal force. That is what the scale is measuring. If you stand on the analog scale and you bounce up and down, your weight is not changing. The scale reading is changing, but the weight is not changing. There was another comment that I heard, I just want to address that. Scales measure force, balances measure mass. A proper scale would not give you a value in kilograms. Because the ones that do are making assumptions about the acceleration due to gravity, which are not always valid.
So what would they put it in? Just grams?
That's also a unit of mass. They would put it properly in pounds, newtons, dynes if they wanted to go old school.
Dynes?
Dynes. D-Y-N-E. Dynes.
Huh.
It was the common unit of force till Newton came along. Now, why is it I stand on a scale and they say that's my weight, when it's really just the normal force? Well, let's go back to our equation over
Because
here.
how much pressure you're exerting on the earth.
If I am just standing there, completely still and not moving, what is my acceleration?
Force should equal mass, because there's no acceleration.
That's what that says. But if I am standing on a scale, not moving at all, not about to move, I'm just standing perfectly still, what is my acceleration?
0.
So if my acceleration is 0, my total force is 0. As I look at these two forces, if my total force is 0, then my normal force and my weight are equal to each other. So if I am in equilibrium, those two forces should have the same magnitude. They cancel each other out. That's why we said it measures weight.
It's like substituting says there should be equal. It's assuming that the normal, since they're equal, it's essentially assuming that the normal force should equal weight.
So scales measure normal force. That's it?
Yep. So, there is a video that I have later on where I talk about the differences, because we're not in equilibrium. We're on the Earth, and the Earth is going around in a circle, so our direction of our path is constantly changing. How much does that affect it? Air is all around us. We are in a fluid. That also affects us because air pressure is pushing up on us in general, and so that also affects it. And so things are just a little bit off, but we're going to stick with the nice simplified flat Earth for right now, and we'll get into, well, in physics in general, you start out with the simple case and you just add a little bit of reality as you go. I think we're ready for the next one. Before I reveal what we're doing next, are there any questions? All right. Box on ramp.
Oh boy.
Did you say ramp?
Box
We're about to get some pictures.
on ramp.
I had a box on RAM first time.
That's a harder problem.
Yes, on a sheet.
Now, the way I've drawn this is my ramp. The ramp and the Earth are part of the same thing. It's a slightly more complicated problem if I draw the ramp as separate from the earth, but for right now, we'll just keep the ramp as part of the earth, and I put my box on the ramp, boom. Now I separate the drawing. My recommendation is to try to draw things in the same orientation that they are in the problem. Some people will straighten the box out, which is not inherently wrong, but people who do that tend to make another mistake. And I think it's just simpler to keep things in the same orientation they are in the problem. Can we
There's
get
no
rid of anything?
friction.
Pardon?
There's no friction.
No, it shouldn't be.
There is
Wait, what?
If I put a box on the ramp, is there, if this ramp is frictionless, is that box gonna accelerate?
I thought it was in the air.
No,
I was looking at, sorry, then there's no tension?
no tension.
No,
Shouldn't be
No other.
That's all.
Okay, 40% of the problem gone. All right, so let's do friction last, since that's the new one. Gravitational force. I saw the hand gesture back there. I assume that was the intent. Now, this weight arrow acting up, I drew it sort of in the ramp, but really it is on the planet itself, so anywhere down here is fine for drawing this weight arrow. I have only one small object, so gravitational force done. Normal force. Let's see if people will fall for rookie mistake number, whatever we're up to. Which way is normal force acting on what?
They're pulling away from each other. Not that, like the arrows are going in opposite directions.
That is true. Which way is it acting on the box?
Up. Up.
What was the, then I erased it. What was the direction with respect to the objects?
Okay, so it's going
Perpendicular.
like that.
Perpendicular.
Yeah, the surfaces are this way.
So it's diagonal?
The biggest mistake I see students making is drawing automatically normal force opposite direction of weight. It is not automatic. Forces come in pairs. What's the other part of that pair?
This way on the ground.
We still have to put subscripts. Are we gonna do that later, or should we do
You
that
shouldn't
now?
have to, it's just two objects.
I have only one small object besides the planet.
Oh,
I
okay.
have only one small object and a planet.
So technically you could, you just don't have to.
Right.
Okay,
Because we're not gonna be dealing with multiple pairs of gravity.
alright.
And, oh, that's it for normal force. All right, friction. That's right, which way does friction act?
Would it be like this?
Parallel with the ramp.
All right, so
This way.
it's parallel to the ramp. So which way is it acting on the ramp, which way is it acting on the box?
Well, the box should be sliding downwards because
This
of
way in the
gravity.
box, this way.
They're opposite?
Yeah. It opposes the desired relative motion. So the box wants to slide down the ramp, and the ramp says, not on my watch. I'm gonna try to stop that.
Okay.
So it's acting up on the box and down on the ramp. Now notice that I have this cluster here. This is not necessarily clear. If a student did this, I'd sort of roll my eyes and then try to figure out what the student intended. So I'm gonna try to draw it better.
If they were clustered like that with different colors, it's still.
That'd be so much nicer than what I just did.
It's isometric form.
So-
That's
so-
wrong.
So you're using the same colors to make sure the arrows are crossing.
Yeah, I'm trying to draw it so it's clear. Now, I understand you draw and sometimes it ends up that way. If you happen to notice, it'd be nice if you sort of make it a little bit easier for me to read.
Remind me, So the F arrow on the box,
And you push
as
the
in
sword.
friction arrow on the box.
Yes.
That's for the box or the ramp?
That's the force acting on the box. That's what the ramp is doing to
Is the
it.
ramp the one that
Okay.
is stopping the box, or is it the box is stopping the ramp?
Did you enhance like?
Yeah.
Now,
So why is the arrow on the ramp?
You need breakfast?
All right, let's connect this with some of the other stuff that we've done. Oh, questions before I connect it with something else we've done? All right, connected. We go back to F equals ma. In this, I have two vectors, acceleration and the total force. Since those are the only two vectors, they have to be in the same direction. So my total force has to be in the same direction as acceleration. So I know my acceleration is going to be down the ramp. So when I add the three forces, it should add up to a resultant that is down the ramp. So if I needed to add them graphically, I have, let's see, let's go, I'll do normal force first. And I have normal force acting this way, my weight is acting down, and friction is acting up the ramp. So if it accelerates down the ramp, then my total force would be that. The white arrow is my total force. If there's no friction, then my total force is an arrow pointing all the way down to here. If it is sitting there and stays on the ramp, then my normal force, or then my total force is, well, non-existent. I have a triangle. Friction would come up to here.
So arrow going up is Y, normal force. Arrow going at a negative slope towards the ground. Now,
All right, they're gonna match the same direction as I have over
the
here.
arrow that goes completely
that's
down is
normal force.
is gravity.
Weight, friction, and then total.
Okay. Thank you, because I only got pencils.
That's the word net. Net force.
Let's just start bringing my
There is a